Hey, how you doing? Hi, Jerry. As soon as we get a few more in, I will tell you what's going on and what the new modus operandi is going to be when we do our nighttime sky views and our sky tours. So, I'm just going to wait a few seconds here, a few minutes. Hi guys, welcome to the SkyTour LiveStream. I'm currently on a globular cluster in the constellation Lyra, and this globular cluster is one of many that we have in our galaxy that is surrounding our galaxy in a halo, and we're going to continue to look at these objects. I solved several problems that were occurring in previous streams. The other night you might have noticed that the images on the screen sometimes would turn vertical. That had to do with when the camera was on its side, it thought I was doing a portrait, and so it would flip the thing upright instead of horizontal, so I disabled that, which is kind of good. And Ian, I'm sorry you can't stay longer, but you know what? You got to get your training done. And I'm okay with that. This is always going to be available for you to watch at another time. So thank you for stopping in, actually. That's very nice of you to do that. You didn't have to. But I'm glad you did. So you see this globular cluster here, and I'm actually going to go and we're going to do a number of objects kind of all in a row. And then what I've done is I've done this little extra thing, and that is I've added an image processing application to my computer out here in the observatory. And after a while what we're going to do is we're going to take the photos off the camera right into the computer, and then I'm going to share my screen, and you're going to watch me image process them so you can see what you can get by taking just one photo of an object. And I think that'll be pretty cool. So we'll try that a little bit later once I get going here. Oh, hello Heidi, I see you out there. Yes, Heidi was on the phone with me earlier just bugging the crap out of me. Yes, I'm kidding. So, let's see, we've got 10 people in right now. We'll just give it a shot and give it a little more time. You guys are the regulars, which is great. Heidi, if you're going to stick around, let me know. You can mod for me, because you know these people over here, these guys are really, they get out of control so fast. That's a joke. So, I'm gonna try and look at a couple of things right here that I think you may like. We don't have a moon for a while, and that's good. Okay, this one is something that we've seen before. It's called Messier 66. It's it's a spiral galaxy in the constellation of Leo, and I think that it's really cool because when we look at Messier 66, you know, it's 37 million light years away. And to give you an idea of what a light year really is, a light year is 6 trillion miles. That's the distance light travels in 1 year. A light year. Now, this light year concept is interesting because when we talk about measurements on the Earth, we measure in miles, we measure in feet. And when we get down to really small things, we measure them in microns and so forth. But, you know, globally, we measure our height in feet or in centimeters. We measure distance in miles or kilometers. But when we actually get out into the universe, those units quickly fall short of being satisfactory because the numbers get so big so fast. For instance, light speed. Light speed is 186,000 miles per second. That means that speed, light could go 7 times around the Earth in 1 second. That's fast. But it's still slow on a cosmic scale. What I mean by that is, the nearest star is the Alpha Centauri system, which is actually 3 stars. Alpha Centauri A, Alpha Centauri B, which are kind of similar stars. And then Alpha Centauri C, which is a red dwarf circling both of those, orbiting both of those on the outside, on the far outside. And that's the dwarf, by the way, around which we found the planet. Now, those stars are all 4.3 light years away. 4.3 is actually the distance to Proxima, which is that component C of the Alpha Centauri system. So those 3 stars, we're talking about Proxima now. 4.3 light years is the distance to that star. That means it takes light to get here from the closest star to us. 4.3 years. Light speed is not fast, folks. Light speed is slow when it comes to this. So the concept of light speed is one that is important to understand. So when we talk about a galaxy like the one we're about to go to, a galaxy which is 37 million light years away, that's 37 million years ago. That's halfway to the Cretaceous Paleogene extinction event. You know, what they used to call the KT event, or the asteroid that killed the dinosaurs. That's more than halfway to that event, in time. So that's how long it took the light that we're going to see from this galaxy to get here. So let's go check that galaxy out. Okay, and let me just get the camera set up here and do that. Okay, so now I'm going to just take a photo so we can see it. And what we'll do actually, when we come back in later, we'll come back in and we'll actually take these photos, like I said, off the camera card and look at them on the computer and then do some image processing to see if we can make them look better. So, this particular, there it is right there. This galaxy is actually pretty interesting because at that distance this galaxy is, it's like I said, 37 million light years away. That's not close. It's actually quite far. And there's a lot of interesting things. Amateurs and alike have been looking at these galaxies for a long, long time. The galaxy is in the vicinity of several others in the area of it. And the interesting thing is that if we combine all of their starlight and put them together in one spot in the sky, they would be almost as bright as the sun. Okay? But because they're so distended and so far away, we don't see them that way. And that's really kind of, that's a fact to understand. And there's actually a gravitational interaction between these galaxies, this one here and the others. And it would be nice if you could actually see the galaxy, right? So I guess I should bring that up. So yeah, and you can actually kind of see a little bit of the spiral structure. And I'll kind of zoom in a little and help you see that. See, we don't have a moon yet tonight, so we can actually see some structure. You see that? That's pretty cool. And we'll do a little work on that in a little bit when we get it into the computer. So, you know, this is one of those things where we actually see an object in the sky, and it kind of looks like it does when you do some image processing on it, but it's really quite nice on its own. It stands alone as a really pretty object in the sky. So let's take one more photo of this. All right, and again, this is Messier 66, and I introduced you to the catalog called the New General Catalog, NGC. And NGC is another thing that we, another catalog that we use and that we discuss when we talk about looking at the sky objects. And this is NGC 3627 by that measure. So I have it as an ISO or an ASA, a sensitivity of 12,800. I'm going to go down to 8,000 and then go up to 20 seconds on the exposure. This would actually give us an identical photo of what we saw, except with less noise. So let's do that. The galaxy will be just as bright, because what we lose by going down in sensitivity, we actually go up, you know, in the exposure, and that gives us back what we lost in the sensitivity. It's a one-to-one relationship there. That's what's cool about cameras. That's something that you can take away from all this. So again, this is Messier 66, and let's take a look at it. Again, let's zoom in. So you don't notice, okay, there's sort of a pink cast to it because of the nature of the sensitivity issue on the camera, and that's fine. It's not doing anything wrong. It's actually doing exactly what it should be doing. All right, but the interesting thing here is this galaxy is really very close to several others, and I know that when we looked at this one other night, and I'm trying to remember if we actually saw the others in the same field. My inset image is probably in the way. Figures. But not to worry, we can always go through it and find it. So this, if we want to talk about the actual diameter of this galaxy, based on its distance, all right, which I said was 37 million light years, when we do a measurement of the length of it in what are called arc minutes or fractions of a degree, then we find that it's actually about 75,000 light years across as a galaxy. So, you know, the Milky Way galaxy is just about twice that or so in diameter. Our galaxy is not small, but it's not the most massive galaxy either. There are galaxies that ours would fit right inside with no problem, especially some of these giant elliptical galaxies. So galaxies like this are not really that rare. These are sort of the common type galaxy. So that's Messier 66. Now we've looked at one of these guys, but we're going to go now to this next object, which is a double star in the constellation Lyra. This is a very pretty double star. This is actually called Chiliac. It's actually it's right below the Ring Nebula. Actually, it's right basically above the Ring Nebula. There's actually in Lyra the Harp. There's actually Vega, and then to the right there's two stars that are kind of separated by a little bit of sky, and they're about as bright as each other. And one of them is Chiliac, and the other one is down below. It's actually Sulafat, which is the other star in Lyra. And those actually form the border, the line, and in between them is the Ring Nebula. So this is a double star that is very popular, and it's actually, if you notice, you see other stars in there, and those other stars, we'll talk about their color in just a minute. But basically this one, it has also components you can't see. Again, as I said, it's called Chiliac, and it has components you can't see, and it's called an eclipsing binary. So that means that there's actually a star that's so close it goes around, and because we see a change in the spectrum of Chiliac every now and then, we know that there's something crossing in front of it that's not a planet. It's actually another star, you can't resolve them, that is, show them as two separate stars with a regular telescope. Now I realize you're seeing what looks like 4 stars here, all right, but this one, the bright star Chiliac is there in the center. The 2 stars above are not involved here. Those are actually just background stars. But the one below is actually a slightly dimmer star than Chiliac, and it's actually a double star to Chiliac. It's the component, the binary component to Chiliac. There is a smaller star that is closer to Chiliac, and it's actually orbiting Chiliac itself. So in a sense, this is a star system with 3 stars in it. It's sort of like a planetary system with stars, without any planets. So it's kind of cool, and this is a very interesting double for that reason. You can see the double in the binoculars, you know, and when we talk about the actual types of these stars, the star is actually what's called a type B. We talked about the various types of stars, if you recall. There's O, B, A, F, G, K, M, and this star is a B-type star, but it's a late B. It's a B7, and it's actually the main component of the binary system, obviously. And the second one is a smaller one. The smaller one down below is actually an A-type star. So there's O, B, A, F, G, K, M. Well, the B star is Chiliac, and the A star is the one just below Chiliac, which is kind of bright. All right, and we'll take a photo of that. Not a long photo. We don't need to. Just take a short little 2.5 second photo at 8,000 ASA, just to see the background stars around it. And there we go. It's pretty. And we'll do our trick to check the colors of the star. So now some of you already know what I'm going to do. I'm going to change the focus a little bit. And this actually points out how different the brightness is, incidentally. You can see Chiliac, that B7 star, is actually very bright compared to the A star, which is just below it. Here is where you actually see the major difference in the brightness. When you see them as the stars that they are, when you see them, you know, like this, you can tell there's a difference, but it doesn't really look that profound. But take the focus out a little bit, and look what you got. I mean, it's very, very different, markedly different, which I think is really interesting. Now, one of the things I wanted to mention, and this may happen sooner than later, Darren mentioned to me that he thought I should collimate the scope. That means get that you see that donut in the center up there? That donut is an artifact from the defocusing process, but it's actually a secondary mirror in the telescope. Now, when you have an object centered in the view, that black disk should be centered, and you can see that it's not quite centered. That means that the telescope itself is what's called out of collimation. So I have to collimate it. It's ever so slight, but it does need to be collimated. And so Darren was right. Now, it's natural when you move the telescope over a little bit, okay, you see that disk changing slightly, it changes its position. But it doesn't, it's supposed to be dead center when you're in this dead center, and mine is not. So he's right, we do need the collimate. I knew that, and I had checked the collimation ahead of time, and it was right, but now it doesn't look right to me at all. So that could just be from the time we've spent doing this stuff and setting it up. I could have knocked it out of collimation easily. So let's get it back in focus. And it's interesting that we can't even see the other star right now. Okay, let's check the focus. We're gonna zoom way in to check focus, make sure we got good focus. And I don't. I'm gonna get it back. Here we go. I'm just getting critical focus here. Okay. One little tweak. One more tweak. Okay. So there we are. So that's pretty. That's a nice triple star actually. It's a it's a double star that you can see there, the visual double star. The V7 at the top of the two, and the brighter, and the A8 just below it. The other two stars are background stars. So this is interesting. That is a cool little object. And I would like to continue the run. Let's see, where do we go next? We're going to go to this object. This is actually another galaxy, but I want you to see this one. This is the black sky thing. No, it's actually, this is an interesting location because I'm going to show you something interesting here. This is a location where we have a galaxy, but it's actually not a spiral, and it doesn't look like it has any specific shape. And we're going to just take a little, we're going to take 4 seconds at 25,600 ASA. Okay, and we're going to take a look at what we see there. And you see it, it's at the kind of just about the lower right there, and I'm just going to zoom in on it a little, just to show you what we're looking at. That's actually what's called a giant elliptical galaxy. And this giant elliptical galaxy is 54 million light years away. It's actually, and it's immense. This is in the constellation of Leo. And we find that there's a lot of galaxies in Leo. Now, when they say a giant elliptical, this galaxy has, at 54 million light years away, this galaxy has an awful lot of stars in it. But they're in no particular pattern. You don't see spiral arms. It's just a giant mass, an oblong mass of stars. And this is just the way it is. And so if we measure its angular size in the sky, it has a long axis, a length along the long axis of 160,000 light years. That's huge. That's a massive galaxy. Now that's roughly the size of ours in terms of length. This is really one of the giants of the galactic cluster that's in Leo here. A little earlier, by the way, just a totally non sequitur here. A little earlier, I got an alert on my iPad system here. It said the ISS was rising, and I looked right out the dome, and boom, there it was. It's beautiful. It was just coming up and coursing across the sky, and we got to wait 90 minutes to see if it'll come back. I'm not sure, but we'll find out. Anyway. So this is the giant elliptical, and I think if we take a zoom in here, you can see that there's actually a little object next to it on the left, and that little object is actually it's actually a foreground star, as it turns out, and that foreground star is, you know, here in our galaxy. So it's actually 54 million light years past that, you know, past that star, well, 53 million light years past that star approximately. So, you know, we're looking at you know, a three-dimensional universe in a two-dimensional way. So it's kind of hard to actually see the galaxy in this way, to see it as a three-dimensional universe to us. It's not easy to see that. Let's see where we're going to go now. We did that. We did that. Okay, let's try this star. And we're jumping all over because I want to. I just want to jump around tonight and have some fun. This is another double star, and I think that this is going to be pretty cool. Okay, this star is actually fairly nearby. It's actually not very far away. And let's just take a photo, a 4-second photo at, let's see, let's take it at 16,000 ASA, 4 seconds. So the screen goes black for a minute. 4 seconds, that comes back. Okay. Now, now I had said that this is a double star, and they are. It's actually a double star, but the problem is this one, like some of the others that we've already looked at, like the double in Lyra, the components, the two stars, are actually so close together that they look like they're just one. And when we zoom in on this, we can't even see that second component, and that little tiny star just above it, okay, is not it. So I think it's pretty interesting that we, you know, when we try to find this, it's kind of impossible. The stars are pretty much the same type of star. They're both main sequence, which means they're both burning hydrogen into helium normally, and but because they're only 25 light years away, so it's kind of interesting because it's we're unable to see the two components because they're so close together, and that's kind of, and I guess you have to take my word for it, huh? You don't know. Now, the other fascinating fact about this star system is, like Epsilon Lyra, the double-double, this is also a double-double system, and you can't see a single one of the components right here. And that's because the star is actually got another star going around it, and each of those two stars has yet another star going around each of them. So it's a wacky dance they're doing out there. It's really cool. And this is, you know, this is kind of tough, you know, because we don't really, we don't really have the ability to see with this is a more rich field telescope, and we don't really get to see a whole lot of the interactions here, you know, like that with the telescope like this, but we can see some of them, and that's kind of what we're going to do. We're going to revisit this in the future when I get another capability I'm planning. So I'm not going to tell you right now because I have to make sure I can get it. Now, let's see. We're kind of going on this little hunt here. Alright, this one, Yeah, we might go on this one. We might look here. Yeah, maybe. Alright, we're just going to go to this one, check it out. Okay, we got our beep. So we're going to take a 4-second exposure at 16,000 ASA. And there it is. That is actually called Virgo A. It's a, oops, sorry. That's Virgo A. Virgo A is a another giant elliptical galaxy, but Virgo A actually is one of the largest galaxies that we know in terms of elliptical galaxies, and it has a jet that comes out of it. That's actually it has a giant jet, and the overall view. This is This is M87, Measure 87. The jet of material that's coming out of M87 is really quite interesting, and it's something that we can't see readily right now, but it was discovered back in 1918, and it's like a straight ray coming out of it. That's how it was described when it was first found, and it extends out of the bright nucleus. Now we can probably try to get a better view of this and try and see it. But the interesting part is that when we look at this guy, it's nearly spherical, and it doesn't quite look that way here, but it is nearly spherical. And I want to take another photo a little deeper so you can see something here. Okay, so this is 10 seconds at 16,000. So we'll let that go and see what we get. Okay, now the thing to understand about this galaxy is that, like ours, okay, and like other galaxies, this one also has globular clusters like ours around our galaxy. We actually have globular clusters around this galaxy that are present. We can't see them readily, but it has a number of them as well, and it basically has a far greater volume than our own galaxy, this little guy. And I say little guy, it's 55 million light years away, and it actually is about 120,000 light years across. But it's a sphere. It's spherical. See, that's different from ours, which is disc-shaped. So a disc-shaped galaxy that's 120,000 light years long doesn't have nearly the volume of a spherical galaxy 120,000 light years in diameter, you see? And that's something that is important to understand. Drink break. Just taking a little sip of water. And I'll be cracking open the raspberry Snapple in a little while. Now, in this image that we took, you can actually see the jet. Do you see it? It's emanating, it's coming out of the center and heading a little bit to the right. Do you see that? That is the jet. It's part of the famous jet of this galaxy. So there's a lot of detail to that jet, but we can't see it with this telescope. You know, Earth-based telescopes are kind of inadequate, but the Hubble Space Telescope shows a beautiful view of that jet. And you can see the jet. It's just coming out a little bit to the upper right and heading to the right. Alright, so that's why I wanted to take the longer photo so we could see that. Very cool and very interesting nonetheless. So let's go and keep the hits coming. Let's see. Where are we going to go next? We went to Epsilon Lyra yesterday. let's go. Actually, we're going to go with this familiar one. This is familiar, but I want you to see this and see it in a new light. No pun intended. Okay, you all actually know this star, whether you know it or not. This is called Vega. It's Alpha Lyra. It's the brightest star in the constellation Lyra. That's why it's called Alpha Lyra. We have Greek alphabet names for these stars, and if you think I don't know the Greek alphabet, some of you have heard me. I can say it. I'll look right at the camera. It's Alpha, Beta, Gamma, Delta, Epsilon, Zeta, Eta, Theta, Iota, Kappa, Lambda, Nu, Mu, Rho, great. I figured I'd screw it up. Okay. Alpha, Beta, Gamma, Delta, Epsilon, Zeta, Eta, Theta, Iota, Kappa, Lambda, Mu, Nu, Xi, Omicron, Pi, Rho, Sigma, Tau, Upsilon, Phi, Keep, Psi, Omega. See, I can do it. And we measure using alpha, beta, gamma, etc. In descending brightness of a star in a constellation. Now, Vega is interesting because Vega being the brightest star in the constellation Lyra, Vega is sort of a candle for us, meaning it's a candle for what's called luminosity and stellar type. Vega is an A star, okay, so OBA, FGKM, A. Is an A0 star. It's also burning hydrogen into helium normally, like our sun is. So it becomes what's called a luminosity class 5, as in V, Roman numeral 5. So it's an A0V, A05, normal star. And that standard candle is one that we use when we measure spectra of other stars. And I think what's interesting about that is that this standard candle is one that we use for doing spectral analysis. I use Vega when I take spectra of other stars. I compare it to Vega. I also use Vega to calibrate spectral equipment. And when I take spectra with this telescope, I actually, instead of the camera here, I attach a camera that has a full range of a full spectrum camera that allows you to see a little of the ultraviolet, a little of the infrared, and all the visible. And we actually can see the spectrum of the star in a much more complete way. And Vega has very, very strong lines in it that are called absorption lines that show these vertical lines at regular intervals that are spaced exactly so in exactly the same position every time. They're in the same position every time because they're part of the hydrogen lines that you see in a star's spectrum. You have Balmer series, you have the Lyman series, and the Balmer series shows very brightly in Vega. And in these A stars, those hydrogen lines are their brightest. And when I say bright, I mean darkest. They're like dark lines. They're called absorption lines. So we're looking here at Vega. Now Vega is 25 light years away. All right, so we're seeing it as it was 25 years ago. And it's a blue-white star. It's, like I said, it's an A05. And it's basically one of the closer stars to Earth, which is probably why it's bright enough in our sky to be seen very well. But there's something else I want to talk about, and that is each of the stars we see in the sky are moving in the sky. Nothing's standing still. So whereas the Earth is wobbling on its axis and doing this precession dance like we know that it does every 26,000 years, the pole is moving around. Vega used to be the North Star thousands of years ago. And then Thuban, which is a star in the constellation Draco, was the North Star thousands of years ago as well, as the Earth continued its little precession dance on its axis, wobbling around. Well, that axis kept pointing, all right, pointing to different stars in the sky. Well, Vega was one of the stars it pointed to at one time. And you know, when you look at Vega, it's so far from the pole. You go, what? That was the North Pole? And yeah, it was. So it's really, you know, it's really the kind of thing that I think is really important to understand. And let's see. Okay, Dave's asking me a question here. The A7, astrophotography, A7, yeah. This camera, the A7S II, is actually well suited to astrophotography as long as you know how to deal with the noise, Dave. Make sure you tell them that the noise is fairly high on this camera. So going back to Vega, we were talking about the motion of the stars. They're actually orbiting the galaxy, as is our sun. But Vega has a motion against the other stars that is detectable, and we can see it every as we look at it, over intervals of years, we can see that it is moving. Now it takes many years to circle once around the galaxy, millions of years for stars, and so when we look at this Vega, we actually see that Vega has a high relative motion against the stars in the background, and that equates to what is and I'll give you the number, and then we can talk about what it means. It's actually 0.328 arc seconds per year. Okay, an arc second is a very small amount. An arc minute, okay, there's 60 arc minutes in a degree, and there's 60 arc seconds in an arc minute. And the motion that Vega moves across the sky is 0.328 arc seconds per year. So a third of an arc second per year, basically. So it doesn't seem to be moving very quickly, you might think. However, it really is when you consider that over the course of millions of years, that star is going to appear to go racing across the sky if you saw it all at once. So, and more distant stars will not seem to be moving as much, and that's part and parcel with understanding astronomy. Everything is in motion around you. Nothing is sitting still. Absolutely nothing is sitting still. So, in astronomy, we always have moving targets. I remember using a special German chart when I was doing my thesis for I was doing a thesis on B stars, the OBA, OB stars. B stars, I was doing a thesis a research paper that was showing how these B stars, some of them, were actually racing out of the galaxy at high speed, just going right out of the galaxy. And I made that discovery using actually some old programming that was available, and I ran these old programs against the stellar data that we had, and it turns out that there were these B stars racing out of the galaxy, and I found a number of them. So I thought that was pretty cool. But you see, nothing is sitting still. There's nothing static, nothing. And if you go right down to your atomic structure, your hand is made up of atoms, of course, not sitting still. They're vibrating at a particular frequency, and that frequency gets changed by other stimuli that come up to you and affect you. So basically, you're in a universe that's never sitting still. If you wanted to actually sit still, you can't. You cannot sit still. It's absolutely impossible. So I'm thinking that it's just it's impossible to understand this. Thanks, Ian. Thanks for coming in, and I hope you have good training. And thanks for coming. So when we look at Vega and the way it speeds across the sky at 0.328 arc seconds per year, we have to understand and remember that all the stars are doing this. Every star you see in that field right now on the screen, every one of those on this live view are racing across the sky at huge speeds for them and at their distance. If you were truly sitting still and you saw one of these stars go by, you would just go right by you and say, whoa, what just happened? And it's because it's orbiting the galaxy. And you gotta imagine that the galaxy's gravity has to be absolutely immense for it to maintain and hold between 100 billion and 400 billion stars all in orbit about it. I mean, think about that. That's absolutely crazy. And it's mind-blowing, and I've never been able to really quite get over that. So I just think that it's interesting, and I have a feeling that we're gonna be able to see more stars like this. I actually want to show you another star called Barnard star. It's actually one of the closer stars. It's the second closest star to us besides the Alpha Centauri system. And Barnard star is one that we should actually go to. I should find that right now, because that's one I wanted to show you before, and I didn't do it yesterday, and I meant to. Because tonight we're taking a tour of the sky in a little bit more completeness. Starting to get the bugs and the kinks are worked out, and it's starting to come together a little better. So I'm pretty sure that this will be good. All right, let me look up this. There we go. I'm just looking for it here. So don't mind me. The problem with looking up Barnard star is that there's also a catalog called the Barnard catalog, and the Barnard catalog has a bunch of objects in it, and they're usually double stars, and so it's tough to find Barnard star in the listing. When unfortunately, I can't see that there. You know what? I will find it. I can find it. And while I'm finding it, I'm gonna get something else here that we can find, just so that I can keep it moving. I will find it. Oh, interesting. Okay, we're gonna try this object and see. I'd like to see if we can find this. This is actually another object that might be interesting if we can see it. Alright, we're going to do a 10-second photo at 32,000 and to see if this is going to be visible. Then I'll tell you. Wow, how about that? There it is. Alright. You know what that is? That, my good friends, is a comet. There was a comet traveling through the constellation of Botes, and it's actually a comet. It's called 2015 V2 Comet 2015 V2 Johnson, and it's in Botes. It's a 6th magnitude, meaning it's not that bright, but it's not it's not that dim either. And so you're actually looking at a comet. Now, what's interesting is this comet looks like it's actually a galaxy or something, but it's not. This is Comet Johnson. Now let me just do a little bit, and I'm gonna kick down the ASA because I'm gonna try and remember to bring Comet Johnson in to see if we can actually do some image processing on it later. I'm going to 8,000 and I'm going to go up to 15 seconds. So I'm at a sensitivity of 8,000 for a time of 15 seconds. Now, some comets can move so fast against the sky that when you see them, your telescope is following the stars, but it's not following the comet. The comet has motion all its own. And in a certain period of time, that comet might appear to be blurred, believe it or not. This comet isn't, because it's actually pretty far away. This actually this comet is actually it averages a distance. It goes out to about 920 astronomical units, which is 920 times 93 million miles. And when it does, it actually that's its average distance. Now let's zoom in so we can see it. Yeah, at 8,000, see, it's a little better, and we can actually check it out. Now you can see that it has a halo, that halo around it. That's actually called the coma, and we don't see a tail, do we? Now there's a reason for that, and that reason is that it's really not that close to the sun yet. Comets don't get tails unless they're like really close to the sun. So I think it's pretty neat that we actually had a comet, and it's actually, it doesn't come toward us. It actually orbits the sun, well outside, far away from the Earth. It doesn't ever come near us. And comets, when you look at comets, what we can do is we can get their spectrum, and we can see kind of what they're made of. And I think it's pretty neat. And yes, and David Schmidt, these are crickets you're hearing in the background. You're also hearing frogs, because I live above a lake. So we actually, you hear the crickets and the frogs. So it's a really nice night noise here. But I think it's just pretty looking at this comet. And hopefully you agree that it's kind of cool to actually see a comet. Now, I'm going to do one more photo. And I'm going to stay at 15 seconds, but I'm going to drop it. Well, I'm going to go down to 4,000 ASA. And I'm going to actually go up to 25 seconds. I just want to, the reason I'm doing this is because when we bring this in later, I want to be able to take it, and I want to be able to process it without a lot of the noise. And we're doing simple processing tonight. We're not going to take it into, other products. I have a number of products that were far more expensive, and I'm going to bring it in to a free tool now that I'm going to tell you about and teach you how to use, in fact, if you want to. Because I teach this in my classes. I teach on image processing. So this will be, this will probably be the one we bring in. There is a slight red cast, and I think that's. I wonder if it was had a slight red cast because I did I had the dome in the way a little. So I'm going to do one more shot, and it might not be true, but. Some cameras, when you take long exposures, you get what's called amplifier noise, and that noise will look like a little red glow on one side. This camera actually has a red glow that's uniform across the field, which is actually good because that uniform glow is easily removable, and that's something that is very important to be able to do when you're actually taking photos and then processing them later. Especially if we're doing things to them that involve doing something called stacking. Stacking, like stacking boxes. We stack the imagery, and when we stack the imagery, we actually see that we get better detail. So, it'll be back here in a sec. At least I hope. Maybe I'm not sure, they're doing 25 seconds. Did I mess it up? I'm not sure if I messed it up. Oh, dumb. Stupid me. I messed it up. I'm sorry. Now I'm taking it. I apologize. I didn't see stars because I'm in an area of the sky where there's really not too many bright stars. But I'm taking the picture now, so it'll come back in a second. I just thought it was, being that it was a comet that was nearby, I thought it would be a good idea to take it. There we go. So that's neat. And just to see it again, And you'll notice, by the way, that the images are no longer doing that thing they were doing the other day, where they would tend to go vertical sometimes. I disabled that. That was the portrait mode, because the camera has accelerometers, and when it goes to a certain angle, it thinks you're trying to take a vertical format picture, and it conveniently puts it vertical for you. Well, that's inconvenient when it comes to astronomy, so I disabled that feature. Alright, now, that's cool. We gotta remember that comet. Don't let me forget that comet. Now, let's see. Let me get back to my list here. You know, technically, if we were going to see the tail of this comet, if it had a tail, it would have been off to the left here, actually. And that's, you know, we don't see it, but that's not the fault of the camera. It's just the fact that Johnson is too far away to actually have adequate involvement from the sun. Now, let me just see if I can zoom in a little bit more on the coma. It's got some interesting detail, but you see it's really kind of round, and I'm just glad we're able to see that. Now, if you saw when we visited Comet Gerasimenko, or Churyumov-Gerasimenko, with the Rosetta mission, you know, it was called 67P. That's an easier way to remember it. 67P was an interesting comet because we actually landed a probe on it as the human race for the first time. And that was a comet that showed us all kinds of things, because we landed on it with the Philae lander, but Philae bounced a number of times because the grabber technology was supposed to land and fire explosive bolts into the soil, the ground, on the comet, which was ice, basically, and it failed. It didn't work. And so the lander bounced several kilometers in space over the comet and slowly came down, only being pulled by the very, very weak gravity of that comet. So it ended up lodged in a crevasse, and it was actually found on a Discovery, on a Discovery image. They actually showed the Philae lander lodged sideways in a crevasse. It's pretty cool. Now, eventually, the Philae lander will be freed, because that will sublimate away and the comet will eventually evaporate on the next time it goes by the sun, or perhaps the time after that. It's already looking pretty frail. Neat. So, let's go. Let's go take a look at... And that might be good. I'm just trying to find the next object here. Okay, we're going to say goodbye to the comet for now, and we're going to go right near it. Okay, this is a double star, and what I want to show you about this double star is a really fascinating, thing about this. Let me just bring us down a bit and bring us over a bit. Okay. Now, this is interesting because this star that you're looking at on the left is a double star, and it's actually a pair of stars that have about the same brightness, but they're only an arc second east of another star that we see there, and they're not. They're actually not. They're not related to the other star. I'm just saying that that's the other star we see, but they're less than an arc second from this there, and they're very close to each other. This is actually a pair of what are called A2. Okay, remember OBA, A2, but then that's the type of the star. But then they're type 3 in the luminosity class. Now, what's luminosity class? Stars that burn hydrogen into helium are type V, 5, okay? Luminosity class 5, normal burning stars. When stars stop burning normally and they start to enter different phases of their lives, they enter up to the giant stage, and that's 1, 1A, 2, and 3. And that's above the normal, brightness of the time when they were on what's called the main sequence, when they were doing that normal hydrogen to helium burning. When they start burning other things, they are actually, they move off that main sequence, they evolve away, and they end up growing in size rapidly. So we're actually seeing what are actually a pair of identical A2-3 giant stars in here, and you can't really see them too well. And the stars are only, in their star system, they're only 33 astronomical units apart from each other. Okay, so that's incredible, considering that they're 176 light years away. We'd never be able to see 33 astronomical units separation between the two stars. But the light you see there on the screen, the light from that bright star, that light is actually a combination of the two stars. And if you're in that vicinity, because they're almost identical in brightness and it's the exact same type, you would actually see that these stars are half as bright, because together they make the brightness you see. Alright, so that system is an amazing system, because the two stars evolved to the same point together. Really fascinating, because to get to type 3, to get to the class, luminosity class 3, that's I, 3, Roman numeral 3, they have to run out of the same fuels at the same time, and that's what happened. So they're probably born at the same time, forged at the same time, in the nebula from which they arose. So that's why this star is so interesting, even though you just see one star. And we'll take an image of it, and we'll make it, we'll just do a 4-second at 4,000, because it's not going to really matter. Okay, there we go. And you can't see that star as a separate star, because, again, it's only, the components are only 33 astronomical units apart from each other. So it's literally impossible to see that, especially from their distance. So they're quite far away. Now, I think it's kind of cool if we move along to. Okay, did I just see something go through the field, by the way? Make note of that time, will you? Because I think something just zipped through. Not sure what it was, but it'd be cool to see it. I could have just been seeing things. I'm looking here on my list. Okay. I want to go. I'm going to go to another galaxy to show you. This is called the Sunflower Galaxy. Okay, so we don't really see it yet, and what I want to do to make sure we see it is I want to take an image of it, and let's do a discovery image, basically, where we actually will take 10 seconds at 10,000 ASA, kind of like a just a test shot to make sure that it's in the field, and it should be pretty close. If not, it's got to be there. And there it is. And the Sunflower Galaxy is actually a very nice little compact object that we'll play with and be able to see a little bit more extensively once we can process it a little. But if you'll notice, okay, just in this image, you see there's a hint of more outside detail. It's not just the bright core. You can see that there's some dark edges or some dark elements in there. And this is actually very true for a lot of objects. You can actually see that these objects have much more detail than they're letting on. So what I want to do in this particular case is we're going to come back for a sec. I'm going to take a 20-second exposure at 10,000 ASA, so I'm doubling the exposure. So there goes the exposure, so it's off taking a picture now. And I'd like to see that, I'd like to see this actually come up with a fine result that we can actually work with later. So let's see what we get. It'll be finishing up in a second. There we go. Now, if you notice, that's actually pretty cool. Don't worry about the red glow. We're going to get rid of that. We're going to get rid of that red glow. But you see that? And one thing that's interesting is, as I move it around, you actually see some more detail, the extent of the detail, and it's actually a way that your eye works. You can actually see how your eye can actually be used to see more detail than you thought you could see. So I just think that's really cool. So you'll notice that thing actually has some more detail in the middle. It has a more extensive circular cloudiness that's outside that core of cloudiness that we see. And we'll try to bring that out later on. I'm going to also install some serious image processing tools on this computer, and we will journey in with, say, one good picture of the night or several pictures of the night to do that. This is actually, okay, now as far as the object goes, this one is actually called the Sunflower Galaxy, and it's 29 million light years away, and it's not very bright. It's sort of it's called it's a magnitude 8.6, which to see something with your eye, it typically has to be a 3 or 4 magnitude. This is 8.6, which is significant. Faint stars are magnitude 19, for instance, and a little more. So this one has the 8.6 visual magnitude that we see with our eye, and it has these very interesting tightly wound spiral arms. And you can see the dark lanes in that spiral arms. You can see this that has a dark lane there in that lower, just below the central bright nucleus. You can actually see the one dark lane, and there's actually more farther out. So they actually are, the spiral arms look a little bit grainy, a little bit, but that's how they look, because there's so much going on in there. Now, what's interesting is this is again Measure 63, which is also New General Catalog item, or NGC 5055, with a popular name of the Sunflower Galaxy. It kind of looks like a sunflower, in fact. Now, when we see galaxies like this, we can see many of the face of their stars. It's more face on to us. One of the things that is interesting is that we can actually see supernovas that occur in these galaxies, and we actually saw a supernova. It was in 1971 they caught one, and it actually the supernova itself in this galaxy reached magnitude 11.8, which is faint, but don't forget it's 29 million light years away, and it showed up as a bright dot, relatively speaking. Considering the galaxy is 8.6 magnitude, the supernova was only slightly fainter, and that's actually incredible. So it has a diameter, if you want to consider that based on its size in the sky and its distance. Its diameter is actually 90,000 light years. So this actually is a pretty good system. And it's only a hop, skip, and a jump from M51, which is the Whirlpool Galaxy that we saw the other night. We're going to look at the Whirlpool again because without the moon, it might actually be just a little nicer tonight. and I would like to give it a chance to prove me right. So we're going to go back to the Whirlpool. We'll do that right now. This actually wasn't on the actual journey for tonight. I just wanted to do it based on the fact that I think it makes sense, considering that we've seen it before, and under a moonlit sky. Now let's see it without the moon. How about if I give you a live view? Okay, let's see here. Okay, we'll do 20 seconds at 10,000 again. So, I'm sorry for the time it takes to take the exposures, but you know what? It's fun. And it's worth it. Especially when you see what results. So right now we're going back to the Whirlpool Galaxy, and the Whirlpool is famous, as you'll remember when you see it. You'll say, oh yeah, and now you're saying it right now. Oh yeah, there it is. The Whirlpool is actually a very famous landmark for any astronomer who wants to cut his teeth and figure out where things are in the sky. And so the Whirlpool itself is a face-on galaxy. And if you look tonight, see what happens when there's no moon? Look how you can see the dark structure right near that nucleus and the structure within the spiral arms. Is that not incredible? And that was a 20-second exposure. And that's because we're using these special cameras. Now, our cameras are a little bit different than the standard camera, but we've modified them a little bit to be a little bit more sensitive. And that's not a big deal. It's something that anyone can do. But just to refresh your memory, this galaxy is 28 million light years away, and it's actually interesting because the telescope can show plenty of interesting properties about this galaxy, including supernovas. And the supernovas that occurred in this galaxy have been seen by a lot of people, and it's really comparable to the Andromeda Galaxy in mass and size and brightness, and like the Andromeda Galaxy, which is Messier 31 in the Milky Way, this one has a major satellite galaxy, which you can see up top there. They're called satellite galaxies or companion galaxies. We have two of our own, the Magellanic Clouds, the large Magellanic Cloud and the small Magellanic Cloud. They are companion galaxies to our own, which are little irregular collections. This has got one too. Take a look just above that nucleus. Look at the knotty structure up there. You can actually see a tremendous amount of structure right there in this galaxy, and I think that's kind of cool. And you notice, and yeah, exactly, Rockstar, yeah, it's way better tonight. Sure is. All right, and that's what happens. See, when the moon isn't up, this is what we get, and it's just the beginning. It's actually, you ready for this? It's a rotten night. It's a hazy, lousy night. Okay, that's probably why it's a little bit red, because we're seeing some long-distance sodium vapor lamp glow in our view, and that's something we can get rid of in image processing. Now, we will go through these photos together a little bit later, and then dig through them and pull out the ones that we want to actually see. I think that's pretty cool, and we'll work on them. So, let's do another photo of this, and let me see if we can coax out a little more data. We're going to go for the full 30 seconds, and I'm going to drop the speed down to 8,000, so it'll be about the same photo with a little less noise. Okay, and I'm doing that because I want to be able to get the best we can get out of this object. So are you having a good time so far, all of you in the chat room that are paying attention? Some of you probably fell asleep. I'm kidding. Yeah, look at that. That's beautiful. And when we see this, you know, we talk about this being better on other nights. As I said, this is an example of a hazy night. But look at that galaxy. 30 seconds. 30 seconds. And by the way, 30 seconds highly magnified, and we're still seeing round stars. That gives you an idea how good my telescope is aligned and set up to be able to follow the stars. In order to do that, I had to train the drives. I had to make sure that the drives are trained. And I had to do what's called periodic error correction. And I had to calibrate all the sensors on the telescope to make sure that it was working right. And that part, the observatory was done in less than a week. I had the building up in a week. I had the pier done and mounted, had the telescope in it, in just over, you know, from the time I had the pier installed to the time the telescope was on, it was only a week. So I built the observatory around the pier. So the pier was, you know, here, sticking out of the ground all by itself, and then I built the observatory building around it, and that's what you do. Because there's a hole in the middle of the floor, and then you can jump around and bounce in here. Doesn't affect the thing because it does not feel it. The building is suspended off the ground, and the telescope pier goes down below us, down into the ground. So I don't want to fall through the floor and go down into the ground here, but it would be a small fall, but it would be enough to be damaging. Just taking a sip of my water. So I think that's pretty cool. I mean, I just can't stop looking at this. It's just beautiful, and I hope you think so too. But we have it. We've captured it, and we'll check it out later, I'm sure. And then we can work on it and get some other clues as to how it looks. So let's go back to the live view for a second, and I'm going to drop down the time here a little bit, and let's see here. I'm doing something, hang on, we're doing it together. Okay, this is I'm capturing live video, so you're actually seeing the Whirlpool Galaxy being captured with live video, and it's 4K video, so it's actually very high resolution video, and I can dynamically change the parameters as we go here. I can actually reduce the amount of the ASA setting, which will reduce the noise, see, so it comes down. But this is actually a live video feed right now, right from the telescope. And that's another thing that I don't do enough of with you, and I'm probably going to do some more of. You don't see it in the same amount of detail, but we are recording it here as well as seeing it with a little bit more sensitivity, and that's kind of interesting to us because that can give us more information. And if we can literally go so far that it becomes ridiculously sensitive. And this is actually an exposure of, let's see here, this is 51,200 ASA at a quarter second. And if we come back, you know, this is an eighth of a second, this is a quarter of a second. You can see the difference it makes. It makes a huge difference. And then we just increase the sensitivity, and we can actually see how we can actually get it up ridiculously, you know, sensitive. But there's just so much that a telescope can do for you when you have a camera with this kind of sensitivity on it. So that was just a live video feed, just to give you an idea what that does. So this is the live view without the video feed. This is just a straight view right out of the telescope's HDMI output. So let's let's go to another popular object right nearby. This is called Messier 101, and this is also a spiral galaxy. It's actually got a special name. You know, it's Messier 101, but it's also called the Pinwheel Galaxy. And the reason for that will become clear as soon as you see a photo. And we're gonna take a picture. We'll do 13 seconds at 64,000 ASA. Just for now, we'll change the parameters. This is just a discovery frame that I take. I call it a discovery frame. It's just to make sure it's there. And they give us some information. Usually they're taken with parameters that are far more heightened than we actually need. And as you can see, it's right there in the center, but it's actually, you can see it right there. Okay, and it's actually a face-on galaxy. It's facing us, which is really cool. And the nice thing about it is it's really symmetrical. So I want to try and monkey with the settings to see if we can actually get a nice view of it. So I'm going to go down to ASA 10,000 and do 15 seconds at a sensitivity of 10,000. So now we'll see, for a little longer time, we're going to have less noise, and we'll see what we can see. Now, one of the interesting things about this galaxy is that it has, for all the what appears to be its perfect nature, it's actually got some asymmetry, meaning that it's not quite properly symmetric. That is, the nucleus of this galaxy is actually a little off center, and it's not our fault. It's what the galaxy is. Let me just pop out a little bit here. So it's kind of hard to see it right there, but we'll see what we can do with the image processing a little bit later. It's like I said, it's a spiral galaxy, and it's got amazing properties. It's like 27 million light years away, and we know that. We know that when we look at what are called Cepheid variables in these galaxies. It's interesting that these variables will vary in their brightness, and it corresponds to the distance that the galaxies are from us. It's an interesting relationship that was discovered, and that's the kind of thing that we use to gauge distance to these things. So it's about as bright as the sun if we consider it as one object and brought closer to us. It's called an absolute magnitude. And when you have a face-on galaxy like this, again, you probably heard me talking about this before. Whenever we have a face-on galaxy, what do we look for? We look for supernovas. Supernovae occur in these galaxies because we can see pretty much everywhere in the galaxy. In other galaxies where they're edge-on to us, we would only see one if it goes off near the edge that's facing us. If it's buried in the middle or past the center, or worse, then we might not see it at all. We might not see evidence of it. But when it's looking like this, when we're looking down on top of it, we can certainly see it. So that's what we see, and several supernovae were seen in this galaxy, which is really neat. So let us go to something else that I've shown you before, but I'm going to see if we can see this. I'm going to do a little look. Yeah, we should be able to see this. Okay, we're going to go to a little nebula now. Now, when I talked to you about looking at nebulae, I talked to you about the different kinds of nebulae that are out there. And this is one of those types of nebulae. Now, I'm going to change the parameters so that we can see it just a little less than that brightness there. And we're going to try and bring this down. Let me just do this for a sec. I'll say 6400, and I'll take a 15-second photo of this. You know, that blue color? This is actually a planetary nebula that is a remnant of a dying star, and if we can take a good enough picture, we'll actually see that star in the center. Then it's a faint bluish disk, and that's beautiful. You see, we can actually see that pretty brightly. So I might actually have gone too bright. I might have to tone it down a bit, and I will. I actually went too bright. How about that? So I took a picture which was too good. So let's go down to 6 seconds at 6400 and see if we can catch that central star. It's what's called an 8.1 magnitude object. So it's actually fairly dim, but in this telescope it's actually pretty bright. And once again, it's a little too much, so I actually have to, holy cow. Okay, we're going to go down to 2.5 seconds at 6400. And let's see about now. Is it still too much? Oh no, we're getting there now. We can just barely see it, and I have to just do another, let's go to just a single second at 6400. Alright. As you can see, that's a bright planetary nebula. There we go. Okay, and now you can actually see the central star. Now, again, this is called the Cat's Eye Nebula, and it is a planetary nebula, one that is showing us the remnant of the dying star. You can see that central star left over in the middle, and it's young. It's actually young, meaning it just happened. Recently, galactically wise, and it's 3,300 light years away. 3,300 light years from us. So that's actually, fairly distant. And it has great complexity in that shell of gas you see there. And there's a bunch of knots of gas in there, and the Hubble Space Telescope has shown some really incredible imagery of this thing in there. And one night we'll take some of the objects we've looked at, and we'll do a comparison to the Hubble's imagery of the same objects. Won't that be cool? And you'll see just how far we've come. All right. This telescope is no slouch. This telescope is fairly advanced. And even so, the Hubble is night and day compared to this. I mean, it's just, there's no comparing the Hubble imagery. Or no comparing my imagery to the Hubble. So, now, there's some other interesting features of this thing, and again, it's 3,300 light years away, so we don't really see a whole lot of detail with that central star, but we're thinking that maybe this is the result of another binary system. It might actually be that central star is actually two stars, and they're interacting, and that's been causing this shell of gas around the star. And now, when you look at the very complicated jets of material coming off this object, and you can see them there, they're actually a little bit to the top and a little bit to the bottom right, and in fact, they're kind of in a line with each other. So it's top left, bottom right, but you can actually see those. And this particular object actually is, at 3,300 light years away. That means that you're looking at several light years sloughing off of material there. And that's a fascinating thing to me because, you know, it's an amazing nebula, planetary nebula. Again, they're called planetaries because when Charles Messier in the 1700s was looking at these things, he said, oh, that looks like a small planet. And yes, it actually looks like it could be Uranus or Neptune. And in some telescopes you might say, hey, that looks like Uranus or Neptune. But it's not a planet, but it is a planetary-like nebula, so they call it a planetary. So now, the funny thing is that in this whole process that made this nebula, that actually started changing, and it happened. We think about 1,000 years ago. The way this nebula was making this gaseous cloud changed dramatically, and there's a lot more dust now, and so it's like you know, it started forming these dusty shells, and you can't see the real dusty shells in this photo, but in the Hubble shots you can. And you know, based on their evolution, based on seeing how far out they are, based on seeing what they're doing, it looks like this was probably started and happened around 1,000 years ago, and started happening then. So there are things that happen fairly quickly in the universe, and this is one of them. All right, it's a fairly young nebula, and so I think that's impressive. I'm sorry, I'm reading a message here. Do you think the latest pics from the Hubble, this is Ken Hancock, for the last few years from the Hubble, or are they lying and they're really coming from the Sophia plane? No, I actually think they're coming from the Hubble Space Telescope, and there's a very good reason for that. Because you can see it in orbit, you know, it's going overhead, you can actually see it. In the same way you can actually see and photograph with tremendous detail the ISS. You know, people say, oh, well, there's really nothing up in orbit. Well then, how come my telescope can track satellites, can photograph satellites, and actually see the shape of the big ones? And that's something we're going to actually do when I get that software up and running. I'm talking to people now. And we're going to add an optical tracking system to this telescope. Oh yes, that's right. Optical tracking. We're going to actually be able to track something just by how it looks in the sky. So that would be cool. So no, I think that they're really there. I have no doubt. Not at all. And now I'm just going to take a moment. Sorry about the noise. That's my chair. There we go. Alright, Snapple, raspberry Snapple, made from the best stuff on earth. It's one of the nicest and best drinks there is. So this is a raspberry Snapple. I encourage you to get some. Okay, now let's go back to our plan, and let's go see what else there is. I'm going to go here. This is something that we haven't looked at yet, but I want to look at it, and you'll see it. This is the brightest star in the constellation Hercules. Yes, sir. It's always fun to hear all that noise coming from the telescope. Okay. So this is Rose's spaghetti, or no, that's the funny name we used to call it. This is Rosalgetti, okay, and it's actually the brightest star in the constellation of Hercules. Okay, it's Alpha Hercules, and when we zoom in on it, let's see if we can see. Hello, where are we? Oh, duh. Yeah, I'm gonna take it down a notch on the on the exposure just a bit to see if we can actually see dynamically, see if we can get the see the double. It's a double star, and we're trying to catch this double. Okay, I'm gonna change the focus a little. You just barely see it. It's actually just to the left there. You can actually see the second component. It's close. I'm going to come back out and take a photo at 6400 at 100th of a second. And then let's go in and take a peek and see what we got. Oh, just barely there. You can just barely see it, but it is there. You know, it's another double star, the bright star and the brightest star in Hercules, and you know, Alpha Hercules is actually it's a massive giant. Okay, and it's actually an M5, M5 like Star Trek. Remember M5, and M5 is a low temperature dwarf when it's burning normal hydrogen to helium, but when it's a giant star, this is called a 1b or a 2, IB, Roman numerals 1b and II 2, 2. So it's either a 1b/2 red supergiant, and has a surface temperature of 3300 Kelvin. And Kelvin's related to centigrade and related to Fahrenheit, and you can see that when you look it up. It's like centigrade plus 273, and is Kelvin. So because Kelvin absolute zero is 0 degrees Kelvin, so that's minus 273 degrees centigrade. So take centigrade and subtract 273 and you get Kelvin. Take Kelvin and add 273 and you get centigrade. So those relate directly to each other. Fahrenheit's the only oddball. You have to throw in a fractional value to get the values. So this is a red supergiant, and again, when I say red, what do? We want to actually we want to take and let me get back to the star. We want to jump into the star here in a live zoom feed, and I'm doing zoom so you can see. So there, now you actually see that the star is really a red star. It's actually orange. It looks orange, but it's actually a very red supergiant, and it has a very cool surface. But overall, the brightness of this star is a whopping 7,000 times the brightness of our sun. Okay, it's actually a whopping 7,000 times brightness. So it's a very, very bright star. And it also has that little tiny companion around it. You can just imagine what that companion is seeing. The interesting thing is the companion is also a giant, and it's a G5. Okay, we're a G2 5, and that's as in G2V, as in G2 normal hydrogen burning V, and its component is a G5 number 5 3 III. The G5 and then luminosity class 3. And there's some birds outside that are confused, thinking it's morning. And so it's an interesting thing because the star is actually more than one component. It's two components, and then the second component is actually a binary star itself. So you see, I think you're getting the picture that most stars are actually binary stars. or more, and that's the truth. As a supergiant, the other thing we see is that the brightest, the orange star there, these supergiants actually vary in their brightness, and they're called variable stars. And this is just the nature when they're larger like that. The burning process for the elements that they're creating and burning in their cores are not regular. So there's irregularities in the output of the star. So the star is variable. Now that means that if it starts running out of one particular type of fuel, say it's burning oxygen and making other elements beyond oxygen, say, then if that starts to run out, then the star is going to shrink a little bit, and that's going to actually make it brighter, because it's going to shrink and it's going to actually get brighter. But the luminosity, that is the overall luminosity, is very dependent on the size, the diameter, and the spherical volume of the star, and that drops dramatically when the star starts to shrink. So whereas the star might get brighter, the overall output of the energy looks to get less, and that's something that is you can see if you were to look at the equations for luminosity and how things are related to each other. They vary by many powers. So anyway, when a red giant like this, a red supergiant, actually starts to vary in its core burning and what is burning in its core, it does vary like that because it is shrinking and growing and so forth at a small level, but it has a major impact on its brightness. So most likely this is not, if it was ever, a stable location to have planets, and that's probably a problem. Now Rossel-Getty is also losing mass. Okay, each year it's actually losing mass to the surrounding interstellar medium, so it's starting to slough off stuff. And right now it's only about a 10 millionth of solar mass per year that it's actually losing. But that's not a lot, but again, over millions of years, that amounts to a huge amount. So this star will eventually shrink down to a white dwarf, and it will end up dying as a white dwarf, most likely. So it's not going to have a very violent end. It's going to be like the sun in terms of the fact that the sun will shrink, after it grows to a big red giant, eventually too, in about 5 billion years. So you don't have to worry about packing your bags yet. So I think it's pretty cool. And then so that's Rossel-Getty. I wanted you to see that because it's actually pretty cool. It's a pretty cool bright star. Let's see, and another one that you might like in the same vein is Zeta Hercules. Now we're going to go there now. Okay. It's like the telescope hasn't decided whether it really wants to keep it in the view. Okay. Again, let's do a little trick to see the color of Zeta Hercules. Okay. Now when we look at Zeta Hercules, we see that it's actually it's a fairly bright star. It's magnitude 2.8. And it's the second brightest star in the constellation of Hercules, and it's only 35 light years away. And it basically it has another companion that's only 1.3 arc seconds away from it in the sky. Now, if we take a photo of the right way, we can probably just catch it, but I won't bore you with that. We have other things we want to do. But the thing that's interesting is the brighter star there that you're seeing, that's actually a star that's just a little hotter than our own sun. It's actually a normal hydrogen burning star, and it's actually called it's a G0. It's actually a G04. Okay, it's actually a subgiant. It's actually not like our sun. The companion is more like our sun. All right, the one that we can't see. And a G04, a subgiant, is actually a really still massive star, but it's not burning hydrogen normally as the 5 luminosity class 5 stars do. This is a luminosity class 4, IV, Roman numeral IV. Now, basically, it's about 2.5 times as large as our sun, and it has basically like 50% more mass than our sun. So, it's probably it's stopped doing hydrogen burning, and it's evolving away from that normal type hydrogen burning star. So that's what's going on right here. The star itself is, like I said, it's actually not very far away. It's only 35 light years. I say only, right? Only. I'm reading something here. Ken Hancock saying, that's what I was asking about last night. If you could do that with a galaxy and see the major building blocks. I don't know what you're talking about. You're talking about taking the spectrum? The spectrum tells us the elements, for instance, that are in a galaxy, and we can do that with a star and see the elements that are in the star's, stellar atmosphere. Now, there's certain things, the way things happen. When we look at a star, and I actually did this as a demonstration, because I've done all the seasons of NASA's Unexplained Files, all the seasons of What on Earth, and for some of these, I do science demonstrations, and I show, for instance, how spectra work. And one thing that I showed was how you get different types of spectra depending on what you're looking at and how it's formed. So, for instance, in the star's atmosphere, there's hydrogen gas. But in the outer atmosphere, that gas is cooler than what's underneath it, what's more inside the star. And so that cooler gas, as the radiative energy is coming through it, that cooler gas actually absorbs some of the energy that's coming back that's reaching to trying to get to our eye. And when it absorbs that energy, it absorbs it because it's hydrogen. It absorbs it at a certain spot in the spectrum. And thus we get these what are called absorption lines. They're little black vertical lines in the star's spectrum. And so we can tell what the star is made of based on those vertical lines we see in the outer atmosphere of the star. And in our sun, we see that it's a type G star, and it doesn't have very well-defined lines like that for hydrogen gas. But it does have an incredible amount of lines in it. And that actually has so many, and there's so many different chemical elements in there. In the periodic table, there's calcium, there's magnesium, and there's some very other bright lines in there. There are hydrogen lines. But the fact is, our star was born 2/3 of the way into the life of the universe. So there was plenty of time for other stars to die and seed the interstellar medium with new elements that would form with any star that's born. And our star is no different. We actually formed with a lot of elements already in the star from previous supernovae and from the cloud in which it formed. So that gives us a spectrum that we call the Fraunhofer spectrum, and that spectrum shows a lot of different elements from our periodic table, but they're all at specific places in the spectrum, and that's because atoms give off energy and take in energy at specific locations and specific frequencies. Okay, so we can measure the amounts based on the locations, and the strength of the lines that we see. We can measure whether the star is rotating rapidly, because what happens is with stars like that, those spectral lines, instead of being sharp and focused vertical lines that they're supposed to be, they might be fattened and broadened out. And when you have line broadening like that, there's a number of things that can be causing it, but among them is a fast rotating star can be causing that line broadening as well. So there's a lot of interesting factors and things that you can tell from a star's spectrum, if that's what you're talking about. I'm not sure, but this Zeta Hercules here is like I said, fairly close by, and its companion that we cannot see at this time is a G7V or 5 star. Remember, our sun is a G2 5, so it's interesting that the companion that we can't really even see is like our sun almost, a little bit later type than our sun. Neat stuff, and I'm just very happy that we can play around with this. Now, I think there's another object or two that I want to look at, and just so you know, the moon is up. The moon has now come up, and I think that we'll go take a look at that, because it's now that it's up, it's going to actually interfere. So we might as well look at it and totally destroy our night vision, don't you think? I think that'd be just cool. So let's actually go to the moon. Go to the moon. So here's what we're going to do. I'm going to take us over to the moon. Don't worry, as we go on, as we go later on in the week and whatever, all we need is one relatively cool night where the moon doesn't rise for several hours, if at all, and we're going to be able to see the sky like never before even. And I think that's going to be really cool. You'll like it a lot. I know you will. I really know you will. So let's go now and find das Moon. Or if you have Kerbal Space Program, it's called the MUN. How many people know what I'm talking about? Kerbal Space Program, the MUN. Tell me you know what that is. I will just love it. Okay, heading to the moon. I'm going down to the lowest sensitivity level, and I can see that we have some focusing issues here. I didn't really ever get out of the focus. I'm using it's called the zero movement focuser. It actually is set up so that whenever we look at anything here, it will not move the mirror on the telescope, which they tend to move when you actually focus anything like this. So let's zoom in to get critical focus. And I know you like to zip around when you do critical focus too. That's cool. Let's go just over here a little. Now let's focus you again. And there you go. The way you can tell if you have critical focus is when you actually, when you do focus on the object, what ends up happening is for however far away the object is or whatever, when you focus, you look for a granularity that shows up in the object. It's there for a split second, then it's gone. And that's what we see here. We see that there was some granularity going on there. Now, let's take a look. Let's zip around on the moon. I don't know if any of you actually last night had the opportunity to go back and look through the stream and find that place where that plane crossed the view. Do you remember that? For those that were in here, I don't know if you saw it, but it was really cool. Alright. You know, when people say that the Earth is flat, I just show them, I just come to the moon and I say, wait, tell me that it's flat again? How can you say that when you know, you've got a curved shadow on the moon? It's curved. And seeing a curved shadow is kind of a dead giveaway that you're not living on a planet that has you're not living on a planet that has a flat construction, because you wouldn't have a curved shadow like this. It's curved. So it wouldn't be curved if you're looking at it on a flat Earth. See? It's curved. Curved. So I'm sorry, you know, I don't have very much tolerance for them. You know, there was a exchange that was happening on Facebook, and in the exchange, you know, basically one person said, "Oh, you know, flat Earth people are morons," and basically another person came on and said, "Oh, you know, it's not fair to call, you know, people like that morons. No one deserves to be called a moron." And I actually came in and said, well, actually, yeah, people that, you know, totally abdicate science for a belief with absolutely no evidence, knowingly, okay, and knowingly do that. I mean, what else do you call them? You great thinkers? I think not. Okay, I mean, they're doing like they're dark aged, think free, you know, science free people, and you know, I'm sorry, but if you're not going to embrace the science, then I really have no tolerance, frankly, and I don't have tolerance for people like that. So no, you're not going to get me to basically say, well, everybody is entitled to their opinion. Well, yeah, you can have your opinion, but in the face of scientific evidence, you can't sit back and say, no, that isn't true, that's a lie, that's not this, the GPS satellites are actually on big balloons, never mind the fact that people never see these big balloons. Okay, people at the edge of the Earth, you know, you would think that you would have got a call from someone saying, hello, yes, is this 911? Yeah, my dog fell off. Yeah, if my dog fell off the edge. Listen, you can still hear him. Okay? I mean, where are those calls? I haven't heard those calls. You know? So, you know, I don't think it's worth discussing and going through. But, you know, I know Keith and we did a mock flat Earth battle the other night, and I basically, you know, disassembled them in a few easy steps. I mean, a simple thing. Here's a simple one. When someone tells you that the Earth is flat, you know what you do? You say, well, how does that correlate with the fact that right now the sun is always out at the North Pole all day long, and it's always set at the South Pole right now? And how about the fact that over in northern countries like Sweden and Norway, how come the sun basically never fully sets past twilight? You never get a dark sky right now at that time of the year. How can that happen on a flat Earth? And then they just sit there and go, and they stutter and they complain and they find a bunch of reasons why they think they're still right. See, that's what happens. They fly in the face of actual established science, which is actually something they can learn easily. I actually was talking to someone down below the Antarctic Circle, and at the same time talking to someone above the Arctic Circle. And one was in perpetual darkness and one was in perpetual light. And there I was in Connecticut talking to these two people at the same time and having them describe what they see. Well, right now down in the south it's dark right now, and we have some auroras down here. We got the Aurora Australis blazing in the sky right now. Wow, that's cool. Yeah, that happens all the time, 24 hours a day. We got the Aurora Australis when it's clear. Oh, neat. And then, for the northern person, it was like, well, you know what? We haven't seen this. The sun hasn't set in a long time, and it's probably not going to set for a couple more months, And the bottom line is, you talk to these people, and the only way that can possibly happen is if you're living on a sphere, a globe, a big round thing that's made in 3D. And I think it's really funny, when one of the flat Earth statements that have been made, and I'll be merciless with them, and I do not care, just so you know. One of the statements that was made was this, quote, Flat Earth, we have Flat Earth members all around the globe. Okay, did I read that right? We have Flat Earth members all around the globe. And I think it was kind of cool because somebody wrote in there as a comment, read that back again to yourself, but slowly. Hey, you know what? If the shoe fits. And for them, the shoe fits, but they won't wear it. They'll claim that it's the wrong size no matter what. And that's part of the problem I have with this whole pseudo-scientific baloney. And it's hard when I watch good science be laid barren, Okay, hang on. Let the army go by here. Alright. So, so that is something that's very funny, and I like to deal with it. But only sometimes. Alright, now I'm gonna take another step here, and we're gonna go to the next phase of this. If you're with me on this, I'm gonna take out the camera card. All right, I got the camera card in my hand, and I can turn back on the camera, and we can still stream the moon at the same time. And I will go over to the computer, and I'll put the card in, and we'll play around a little bit and with some of the objects we saw. Okay, now let me just get back in just a second. Okay, by the way, you can't see it right now, but I actually 3D printed a mount for the iPad so that it can hook. Here's the back of the iPad. I don't think you can see this, but yeah, you can. That's ridiculous to think you could. I'll give you some light. Let there be light. So here's the iPad, and what I did was I 3D printed a hook for the back here that you can see, and this hook is actually it's tuned to actually hook into the edges of the observatory, so that what I can do is I can actually come over here, and let's see if I go, where am I going? I gotta go, I had to go over there. It can hook right onto the edge of the observatory, so right now I have it hooked up over there, so it just hooks. And that's kind of cool. So it just actually sits up there, and I can swing it around, I can move it around the side just by giving it a little push. So it actually kind of fits right in. And I had a spider just going down in the web right in front of my computer here, so I had to deal with that. Okay, so let's do this. Turn that light off. I'm now going to put this in and get it. The computer. I'm going to take the pictures that we took and move them into the computer. All right. And that's the first step. I'm going to move some of them and select ones. And I'll have you watch what I'm doing. So I'm going to actually click over to the monitor, and you'll actually be able to follow right along with what I'm doing. Okay, so yeah, there's your chat, which I'll minimize right now just for a sec. Okay, so now so let's go over here and let's see where to go. Put it out, put it back in. Okay, why is it doing that? Okay, it worked fine just a minute ago when I did this as a test. So why is it not working now? Why is that giving me trouble? Shouldn't give me any trouble. Come on, do your thing. Alright, well, let's... Hey, hang on. I'm just trying to work on this, getting this up and running. I'm trying to see why it's not coming up. Should be coming up. Okay, absolutely stupid. That's not supposed to be doing that. I'm supposed to be able to get this. Okay. I had to reconnect it for some reason. Alright, so. Okay, so these are going to be the files that we have tonight. Let's take a look at some of them. Okay. We've got some stars. Okay, we'll go the other way. Got some stars. There's that blue planetary that we saw. And let's see if there's some better views of it that we can get us brighter and brighter still. This was the dimmest one we took. So let's zoom in on this planetary a little bit. Okay, let's zoom in again. And now you can see right there? Right there you can actually see that little bright star. It's right in the center, just off center actually. And you can see that there's some stuff that's on either side of it. Now, let me know in the chat if you can see the screen okay. I need to know that before we proceed. Kind of important. So, are you able to see all this? I'll wait for you to tell me, and then we'll move forward. Okay, so say someone said looks good to me. Okay, good. Awesome. Good, thank you guys. Alright, so now if we come back in here and we look at this one object right here, let's do this. Let's do quickie analysis and just to really quickly try and get out some more detail on this if we can. Alright, this is the free product I told you about. It's called IRFAN, I-R-F-A-N. Look up at the title up there, as it says in there. IRFAN, yeah, I-R-F-A-N view. IRFAN is free, and it comes with some really cool plugins to use. So now you can see that by doing what we did, we can actually see that the star itself, we only just did a little processing on the central block. We can see this now much easier. And that's a really cool little process. But to give you an idea how that worked, okay, compare it to the rest of the view. See how there's noise over here and all this, but now look here. This is a nice, beautiful looking area in the middle. So that's a good thing. So we can do this with other stuff, other scenes. So let's do that. Let's go in and let's go find some more objects that we played with. Okay. Now we took pictures of the stars as well. Okay, so let's go through here. There's brighter and brighter. And then we are here. This was one of the galaxies that we were playing with. Let's see if we did other pictures of it. We did. And okay, and this was the Whirlpool. Okay, Whirlpool Galaxy right there. I'm just finding the best exposure that we took just to make sure we have the right one. Okay, and to find that out, all I have to do is look at our settings. That was a 20-second shot, and I think we actually did a longer shot than that. I think, I'm not sure. Okay, and that's a different one. So that was different. So let's go back and see now where our. Okay, yeah, this is the one I want. Notice over here it says 30 seconds. This is called EXIF data, EXIF, and this stuff is on every single digital photo. Look how much stuff you get. It tells you all about the pictures. Now, if you were shooting with, say, your iPhone, then what you would see actually is a location. You'd get a geographical location down here as well for where you took this picture. So this is a 30-second photo. So let's go in and let's play with this to see what we can do. I'm going to zoom in on a little bit of it right here, and I'll get rid of this EXIF data for now. And let's see what we can do here. So we go into a quickie analysis, right? And I'm going to do something. First thing I'm going to do is I'm going to get rid of that red cast. I'm going to do -2 on the red. You can subtract out red, green, or blue any way you want. Apply to the original. And okay, it didn't do enough, so we're going to do some more. I got all kinds of bugs flying around in here that you can't see, but that's kind of good. And let's do this and take out a little of the blue. I don't want to take out too much of the green, but I think we want to take out, that might do it. That's a little better. Okay, for now that's good. So now that gives us just an area without all that in there. So now let's do this. Now we're going to drop the gamma a little bit and apply the original. Look at that. Look at that. So now we actually have a better looking image. We can drop the saturation a little, which is the color, and actually see it actually helps improve the view a little bit. So now we have that, and now we can also let me try dropping the gamma a little bit more, because you can take it down too much. You know, you could. So let's do that. Let's say okay for that, and then let's actually bring this down to a better size. And now let's do something else. Let's actually sharpen this, so we can actually sharpen the image. Oops, sorry, not save the image, sharpen the image. Okay, so that's actually a sharpening tool. Now, you see in the middle here, you see, look at this dark lane in the galaxy. This dark lane is now showing up perfectly. This dark lane is showing up beautifully. And the dark areas over in this part of the galaxy are showing up. So, I don't know, I think that's pretty cool. You know, and this is what you do after you take the photos, you see. You come in and you do this kind of stuff, you know, and you can actually see it. So now, this is just one shot, remember. One shot. If you do it the right way, then you come in and you take many shots of this, like 10 or 20. And that's what I do. I take many more. And Gene is right. You see how you see more depth basically to this, and it looks good. So if you take 20 shots of this in a row, and then all identical, and then you take dark frames, which are you basically put a cover over the telescope and you take 20-second or 30-second shots. You know. 3 times as many as the light, you know, the shots of the light things you took like this, with the data in it. And then you take very fast shots at the fastest possible exposure. Those are called bias frames. So you basically have the lights, the ones that have the galaxies in them, and you have the dark frames, which are just black screens with the a black screen with the same exposure, and then you have the bias frames. Then you stack all that together, and you end up coming up with a final photo that looks like it's way too bright. And that's the raw data, kind of like an HDR photograph for those who know photos. And then you bring that into a special tool, and you start working on all the data, and you can find yourself getting a tremendous amount of data out of the image, and it looks great. And that's what this is. That's what we're doing here. But we're doing it with one image instead of 20. So it's kind of a cool thing. So what we're doing together now is a little image processing. So this is that particular galaxy that we liked. Now, if we move along to the next one, let's see here. Okay, this one was the sunflower, I believe, and I think that if we bring up the EXIF data, we can see that the EXIF data shows us how long we took picture of for this, and this was okay, down here we see it was 20 seconds right there, and that was 10 seconds. Okay, so basically we took a 20-second photo. So what I'll do is I will take this 20-second photo, and I will again go in and try to find some more detail in the shot. Again, we have a little bit of this glow from the red sodium vapor lamps, so I'm going to kick some of it out right there. I'm going to actually try just doing this. Might look a little blue, but that I can drop a little blue as well, just a touch. Okay, so that's a little better. And now what we'll do is we're going to actually drop down the gamma a little, increase the saturation a little, and say apply to original. And now come back and drop the red a little more, and apply. Okay. And now we have a little cleaner view of this galaxy. You can actually see it. You can see the dark lanes in it quite nicely. And if we then do the sharpening routine that I mentioned before, okay, now we've actually sharpened it a little, and it stands out even more. And you can actually see now when we zoom into it. It still has noise, and that's because we're not using a more powerful tool. I have a powerful tool that will get rid of all that noise and make it look better. And right now we're not using that. So we can see though how we can sharpen and get rid of some of the noise. You can actually see these dark lanes in here. There's more out here. And there's even more out here. This galaxy is actually like this big, and you can kind of see the data's trending that way actually. And with doing a stacked view of all this in here, we would actually get a very beautiful sunflower galaxy here. And that'll be something that I might try on my own just to show you another point. So now, moving along, let's go see. Okay, this was that there. This was the comet. Okay, if you recall, we did a couple shots of the comet. Okay, and I want to actually show you something interesting here. Do you see this? See what's going on? Look carefully. And this is why I took 2 shots. I didn't tell you what I was doing because I wasn't sure it would work, but it did. Look what's happening. It's moving. Do you see that? It's moving against the sky. Okay, here it's in one position, and here it's in another. We actually caught the comet in motion. And because it's in orbit, it's orbiting, the sun at a long distance, but you can actually see that over the few minutes, actually we don't even have to waste time, trying to figure out what that few minutes was. We can see right here that the date and time that this was taken was at 2017, at 9:47, 21:47, 53. Okay, and the next one, let me just make sure we get the right two in here. Okay, this was 9:49:52, and the previous one was 9:47:53. So notice that only 2 minutes went by. Okay, only 2 minutes went by, and we actually got the comet moving in the sky, because they move that fast. Comets are only there for a couple of weeks, and then they're gone. So look at that. There we go. And what I would do is I will go in, and just to do this for fun, we will take down the sky glowing red that we see, and that'll give us more of a proper coloration to the comet head. And let's just do that for this one and save it. I'll save this on my desktop actually, and we'll say this is Comet Johnson 01. Okay, and then we'll come in and do this and get in here and change it to drop down the red a little bit again, apply to original. Okay, and then say okay, to the desktop again. It'll be Comet Johnson 02. I'm doing this in the dark, so that's why it's taking just a little longer to see what I'm going on the keyboard. Okay. So now we have a record of the comet moving, and so now we have our two images of the comet. And let me just minimize this for now, and minimize this, minimize that, and just get to my desktop and get Comet Johnson, get this open. So there we go. Now I didn't pay too much attention to the color. Notice that the color of the comet's core has a bit of a greenish hue. I don't know if you can tell that, but if you look out here with your eye, okay, if you do that, you can actually see that the comet's core is of a specific color, especially here. You can see that it's got a little bit more of a hue that you can see. And if you notice, the stars don't really move that at all that much, but the comet is moving, and that's cool. We're watching a celestial object go racing across the sky. I think that's pretty cool. I'm guessing that we can move on from the comet now. Hopefully you thought that was pretty cool. And then we will see what happens. So, we did our comet thing. Now let's go and pop out of here and pop out of here, because we're done with that, and bring back up our regular viewing. So, I'm just jumping through, see what we got here. Okay, so this was, I'm trying to remember which one this was. I don't remember what this was, but I do know that at probably a good solid 4 seconds, okay. Alright, so we come back. Okay, that's 4 seconds. And that's 4 seconds. Alright. So that's good. So now what I can do is I can go back and we can just do some operating on this guy to see what we can get. So basically we bring up our quickie image processing, and we can drop out the red. Just do it manually, and then bring down our gamma just a bit. And let's see what that gives us. And this galaxy would require just a little bit more effort to work on, and more, so we can sharpen it a little bit, but it's not really giving me a satisfactory result yet, so we'll come back and work on that at another point. Let's see, this one, remember this guy, and this guy was this was 20 seconds at that 8,000. Okay, so let's, I'm looking now, just looking, 13 seconds. Let's see here. Yeah, I don't want to go there. This was a globular cluster that we were looking at before. And images like this are actually very easy to make beautiful, because all you have to do, because they're stars, is you can actually just drop out that background brightness, and look what you can do. And you can even go even more than that. You can actually take the contrast, bring it up a little bit, and then drop this gamma even more. You don't want to go too far, because then you start losing detail. But look at that. That's actually really pretty. So that's another way we can go with these things. And let's see. I shot this of the Ring Nebula earlier before I showed you this, and it was a test, so it wasn't perfect. But anyway, those are the objects we looked at tonight, and I might very well go back and do this again later on. This is my desktop. I shot this image here. This is processed within the special program I was telling you about. So you can actually see the Whirlpool Galaxy as it looks in this telescope tonight. That's what you can get when we do the processing. So I think that's pretty cool. And actually, if we go and get some of these photos, okay, this is the M27, that dumbbell nebula that I showed the other night. You can see that it's really detailed. It's got some detail in there, along with this really faint central star in there. And then this is this galaxy that I just showed you. I shot that right here, and you see how that's naughty. This is what you get when you combine a number like 5 to 8 to 10 of the images. You combine them on top of each other, and then you process them. That's called image stacking. All right, and that's what you get. Isn't that gorgeous? That's beautiful. And then the Ring Nebula. This is the Ring Nebula that I showed you the other night too. That's what it looks like when you stack these objects together. Look how sharp and clear that is. That central star is a pinpoint. It's beautiful. Okay, and that's like a 10-second photo. From 10-second photos. This is what's called the Black Eye Galaxy. I did this one here. We've looked at this. We looked at the Black Eye Galaxy too. And you can see now that when you do this process, you can see that you actually get some really nice detail. And the Black Eye Galaxy actually has a dark lane here and more dark lanes out here. You can actually see all this really delicate detail, you know. So then Measure 81, this is a spiral galaxy. This I did here, and that was actually just a few seconds long. And you can see the dark lanes and the curved spirals. You can actually see the spiral arms here. Very, very clear. And then I did what this is called the Sombrero Galaxy. And there's a very prominent dark lane across the front of the galaxy. It's seen almost edge on. So that's a wonderful thing. I did that, don't remember the date, but it was here. So then 81, 82, these are, 81 is that, and this is Measure 82, which is that starburst galaxy that we look at quite often. And you can see the red areas in here that are actually star-forming regions. It's just an amazing galaxy. So that's some of the image processing I've done here, and hopefully that looked pretty good. As far as doing any more, I think that I'm kind of streamed out for the night. So I hope you guys don't mind, but we're gonna call it. And what I'll do is, after I call it, I'll stick around in here, and I'm gonna actually do a few more photos that we can look at on the next clear night. So hopefully we'll be able to do this again very soon, and I'll get back into OBS now, and you see all this really cool funky stuff as that happens. And we have our moon, and I didn't look in the chat to see if anyone knew what I was talking about when I said this, but if you have a Kerbal Space Program, it's MUN. And I don't know if you have you know about the MUN, but let me bring this back in. Now you might say, if my telescope was so good at tracking, how come the moon was out? And I'll give you the answer to that. The answer is that the actual tracking is very good, but it's tracking the stars. It's not tracking the moon. The moon has its own motion. And the proof of that is when we looked at that comet. And again, I hope you guys understand how amazing it is that we can actually track and see the motion of a comet in the sky. It was moving radically over a couple minutes time. And I think we probably caught it just as it was making a turn in its orbit. So I think that's a neat thing. We caught it just as it's kind of, or it was moving in a perfect straight line, is what I'm trying to say. So from our point of view, it looked like it was broadsiding us, and we got it. It's really good. A little raspberry Snapple break. So I'm going to continue to, I'm going to go back to that comet and take some more photos actually, and then see how far it's gone since the last time we went. Let me see if we can do that. There's actually a number of comets actually that are up there that we didn't actually look at, but that are up there fairly often. I'm looking now. So give me a moment here to look. There we go. No, not that one. I'm still here. I'm just trying to look for the comet. I'm going through my database here. Wow, that's incredible. It's like there's about 300 of them that are visible right now. You know, about 300. That's not bad. It's crazy. Wow. Alright, so I'm going to go back and look at our tonight's best and go through that again, because that's where it was. Alright, so let's go back. Back. I did promise to show you one other thing, which I did not show you, and I'm going to do it. So I lied. I'm not going to stop the stream quite yet. Let's just go right now to this object. I'm set on lunar settings, so that's not good for this. We have to come back a little. So I don't have my card in here right now. I gotta get the card. And it doesn't look like much right now, but we're going to see something in just a minute, I hope. And I'm going to, I'm just going to shut the camera off for 1 second and put the card in, and then turn the camera back on. So just bear with me for a second. That's why I like the second camera, so you can see that there's still stuff going on. Alright. Okay. Okay, 1.6 seconds at 64,000 ASA. Now right there, dead center in that field. You see that little star right there? That little tiny red star. That little red star is called Barnard star. It's the second closest star to us, other than Alpha Centauri system. And it's really quite a fast-moving star. It changes position against the background stars every year. You can see a noticeable difference, just like that comet did over 2 minutes. Barnard star does so over a very short time, over a year. Now let's go back. Let's go to a reasonable ASA. Let's go to say ASA 10,000 and do a 2.5 second photo. So ASA 10,000, 2.5 seconds. Now let's take a look at the second closest star to us. And there it is. It's Barnard star. There it is right there. So there you go. That is the second closest star after Alpha Centauri, and it's got quite a movement in space. That's called that movement, by the way, just so you know, is called proper motion. A star's proper motion is its yearly motion in arc seconds, okay, fractions of a fraction of a degree, that the star is moving against the other farther stars, and that's what we see. Now, what did I just gotta look here at something here. One second, I'm trying to find some more interesting stuff to tell you about. So Barnard star is actually a dwarf star, and it's an M-class dwarf. The interesting thing about these M-class dwarfs is that they're the most populous star in the entire galaxy. There's no more. There's nothing that has. There's no more types of stars than M-type stars. Problem is that not one of them is visible with your naked eye. And the reason is because of the fact that M stars tend to be so faint. Alright? This one's only 5.9 light years away from us, but you can't even see it with your eye. Alpha Centauri is so bright you can't miss it if you can get below, into the southern hemisphere to see it. And it's basically, just to give you an idea, it literally is 3.5 thousandths the brightness of our sun. That's amazing. So that basically tells you the amount of light coming off this star. Yet there it is, we can see it. And it's only got 17% of the mass of the sun. It's literally a fraction of the size of the sun. It's also very interesting because this star is very old. This star doesn't really have any of the contamination in its spectrum. That is the content that's basically indicating that the star was formed when there were more supernovae that spewed a lot of content into the interstellar medium for them to form from. So this star has only 10%, for instance, of the chemical content of the sun, for instance. So it's really kind of Spartan and sparse for that. But nevertheless, that star is right now just sort of passing by us in the galaxy, but it wasn't born anywhere near us, and it has nothing to do with us. It's just a fascinating, star to look at. Now, in the 60s, a guy named Peter Van de Kamp, who I actually learned astronomy from his works. He thought that maybe it had orbiting planets around it, but it turned out those were errors, and there were no planets around it at all that were captured. So basically it's zipping through space all alone without any planets, apparently. But perhaps it has some and we haven't detected them yet. I don't know, and I can't say. But I just wanted to share that with you, and I told you I was going to end the stream, but I couldn't do it until I actually showed you Barnard's star, because I know I promised you Barnard's star. And I also want to try and catch that comet one more time, if we can. I'm just going to be patient with me here for a second. Trying to find it. Trying to find it. Where are you? Still looking. Huh. Still looking for it. I don't know how come I found it so easily before and now it's not even visible in the list. I have no idea. But I do know that we actually caught it in motion, and that's actually really cool. Stuff like that is actually a pretty neat thing, because when we do stuff like that, that actually shows that we can actually contribute directly to the science. And I'm wondering if we want to go here. I'm going to look at this guy, see where it is. No, there's a nebula near the moon that I wanted to show you, but it's too close to the moon, so I can't show you that, unfortunately. Let me look up something else here. 1 second. I knew I'd find it. I found that comet I wanted to go back to. I think it's kind of neat that you look in, when you initially look at the screen, it's like a black screen, but the fact is, it's really not. There's so much going on there. So, for instance, like if we go up and we just pick ever higher, and I'm doing 4K video now, you can actually see the comet in there. Okay, this is in the video. So I'll kill the video now, and it's a good way to use. It's a good way to help spot things too, if you want to. And I'm just gonna bring it over a little more, and then bring it up a little bit, and then I can take a photo. Let's say 4 seconds. No, let's go 10 seconds at 10,240. 10,200 actually. And it'll be bright, but at least we'll be able to see the comet again. Or not. Too bright. Oh, that's right, the moon is up. Sorry, I forgot the moon was up. So what we'll do is we'll do 10 seconds at a lower. Oh, I'm sorry. That wasn't 10. That was 102,000. I apologize. That was 10 seconds at 102,000. So I'll do 10 seconds at 16,000, and we'll be fine. I wonder why it was so bright. Here I am trying to make excuses, saying, "Oh, I don't know what's going on," but it's fine. So we're looking at the comet again that we saw earlier. There it is. I know, you want to compare it to the position from the last time, and so do I. But, well actually, I'll do that actually later on. Save something for tomorrow. But you can see, with that longer exposure, you can actually see that the comet shows some very cool features on that coma around that top. It's actually pretty neat looking. And I'm actually liking that a lot. So I'm gonna wait another minute or two with you here, and then take another photo and do the comparison right live again to see if we see more motion. So while I'm waiting, I'm going to come over here and take a Snapple raspberry iced tea break. I know what you're thinking. You're thinking, he must be getting sponsored by Snapple. And guess what? I'm not. I just like it. So, I'll take another one right now. 10 seconds at 16,000. You know, you can take these pictures and you can actually put them all together and string together a picture of the comet traveling through the sky, along with its tail if there's any, and so forth. So it'd be actually pretty cool. I want to see if we can see any motion on this now. Well, the stars are moving a little bit, but we actually have to align the stars, and it looks like the comet actually did move a little bit in between, you know, compared to the stars. It is moving slightly. So let's come back. Let's take another photo. Here we go. Alright. So now we go back. Yeah, that's the wrong one. Let's get rid of that. Okay, so we get this. Interesting. I'll put them together to see what we have later on, to see if we've got some more relative motion, especially compared to the first two. But I think that's interesting, and I hope you enjoyed seeing that we actually had a comet. Now, what is the comet? You know, the comet is actually basically a cosmic interloper. It's got it's mostly made of ices, and it has some special materials in it that it could be amino acids. It could have hydrocarbons, complex hydrocarbons on its surface. We discovered that with Churyumov-Gerasimenko, Comet 67P. The P stands for periodic, meaning it's going to come back. You know, like Halley's Comet it has a P on it because it's periodic. So, I mean, that comet is actually, you know, as it gets near the sun heats it up and it outgasses and sends all this stuff off, which causes the tail to appear. And there's two types of tails on the comet. There's a dust tail, which is just the stuff that's fallen off and trailing behind the comet. And then there's the ion tail, which is the tail caused by the interaction of comet particles with the charged particles of the sun. And the ion tail always points away from the sun, because the sun's energy is constantly hitting the comet from one direction as the comet approaches, and it sends that ion tail off in the opposite direction from the sun. So as the comet goes around the sun, you know what happens to the tail? The tail swings around with it. So when the comet leaves, it's racing into its tail, its ion tail. The dust tail is still being trailed behind, but that's why when you look in the sky at comets, you actually see that sometimes there's photos of them with two tails. One's going one way, one's going another way, and that's because one is the tail that's caused by the charged particles of the sun. It always faces away from the sun. And one is the dust tail, which is just the stuff left behind as the comet goes through space. So it's cool that you've got these two things going on at the same time. It really is. So let's see. Alright, so I think what I'm going to do is we'll cut the stream now, and I'll come back and probably tomorrow I'll come back and run through some of this with you. Perhaps if it's clear, we'll do some more. But I hope that you had a good time. Thanks for coming. Hit the like button if you can, and if you can't, I'll come do it for you. I'm just kidding. I will talk to you very soon. So thank you for joining me tonight on this journey through the universe on the fifth SkyTour LiveStream. Thank you guys. Good night. Keep looking up.